So I had originally wanted to start with an overview of gravitational waves, but VJ did such a beautiful job introducing them, we're going to skip right to detector noise. So I will introduce you to the LIGO gravitational wave detectors. We'll discuss the properties of their noise, which will motivate a lot of the noise mitigation methods that I'm going to be telling you about. And there are two different key perspectives that I want to cover in this talk in terms of LIGO detector noise. So the first is, how do we improve the sensitivity of our astrophysical searches, particularly to sources of noise that can mimic or otherwise cloud our true astrophysical signals, so transient noise. And then also, a second goal is maximizing the duty cycle. So we'll understand a lot more about why that's important and what we can do about it when we take a tour of the detectors. And then we'll finish with some conclusions. Okay, so here are the basics. So we have space-time strain. So for a gravitational wave that's inbound into the plane of this detector, we measure the space-time strain. So this is little h of t. It's the relative change in length between two perpendicular degrees of freedom over the total length. So in our case, for the LIGO detectors, this big L is 4 kilometers for each one of these perpendicular arms. And it's this orthogonal stretching and squeezing of space-time that motivates the shape of our detectors here. So the basics of how they work is we have some coherent input laser light. It's split by a beam splitter. So 50% of the light will travel in the y direction and 50% in the x. And it will circulate in what we call Fabry-Perot cavities. So these are composed of two parallel optics that circulate the light within them. And again, these are 4 kilometers long. And then the light travels back to the beam splitter. Part of it travels back towards the input laser, and part of it travels towards our output port. So for no relative change in length between these two detectors, we would read out no signal. However, when you have a gravitational wave that's inbound, and you have this relative stretching and squeezing of space-time, this introduces a phase offset in this coherent light. So when you compare the light traveling in one arm to the light traveling in the other, now we can get a readout of our signal. So we're actually measuring photons, so the power of the light in our signal as a function of time is directly giving us this space-time strain amplitude. So that's the basics. So we are going to take a tour of one of the LIGO detectors, and we're going to get a little bit more familiar with some of the terminology and instrumentation that we're going to need in order to understand some of the results at the end of the talk. So we zoom in on LIGO Hanford. So this is in eastern Washington. So again, these arms are 4 kilometers long. And we're going to start our tour by the input laser light. So we zoom into the main building. These are all enclosed vacuum chambers. This is one of the largest enclosed vacuum systems in the world, second only to CERN. And we start here with our input laser light. We call it the pre-stabilized laser, or the PSL. And we inject it into our vacuum chambers. And first it travels through this 3-optic cavity in pink here. So this is called the input mode cleaner, and it serves to select for this fundamental Gaussian beam profile that we need once the light is circulating in the arms. And it next travels to the power recycling cavity, this 3-optic cavity here, which will recycle the light once it comes back from the beam splitter. But for now, it goes straight to the beam splitter and out to the two arms. So we're going to zoom way out and see what the effect is of these Fabry-Perot cavity mirrors. So what you see here is a recycling effect where the light bounces off of the end mirrors of each of these two arms, and it recycles the light up to a factor of 300. So we go from tens of watts to hundreds of watts, I should say, up to megawatts. And now we'll see what one of these mirrors looks like. So here we're seeing one of the mirrors that's comprising one of the two interferometer arms. So they each weigh about 90 pounds. They're isolated with these very, very thin fused silica fibers. So this is the same material that the optics themselves are made out of, and that helps us to reduce thermal noise. So the light makes its journey in each one of these two arms. It travels back to the beam splitter, 50% travels and is recycled in the power recycling cavity, and 50% is recycled in this three-optic cavity called the signal recycling cavity. You should remember some of these names because they're going to come back later. Finally, it's steered into our output mode cleaner and then to our output port. So this gives you a rough idea of what the instrumentation components are within our detectors. So a key message I want you to take away is that it's not just the light resonating in the arms that we're trying to achieve. It's 5 separate independent optical cavities that we're simultaneously trying to keep light resonant in. And this turns out to be very difficult when you have some input ground motion that's shaking the ground around. So we have a full global network of interferometers that are coming online, so this year and into the future. So online and operational right now for the 3rd observing run, we have the 2 LIGO detectors in the US, so in Washington State and Louisiana. We have the sister site Virgo, which is a 3-kilometer detector in Italy. The 600-meter detector GEO in Germany. We have LIGO India. I think I need to actually change this from planned to under construction. That should be coming online in about 2025 at design sensitivity. And then also Kagra. So this is an cryogenic underground 3-kilometer gravitational wave detector in Japan. So what does gravitational wave detector data look like? So we're sensing essentially the relative displacements of our test mirrors relative to each other. So we're comparing the change in relative distance of one arm of our detector to the other, and that gives us a signal that looks roughly like this. So we're seeing the effective space-time strain noise plus signal, we hope, and then versus time. So unlike a lot of astronomy surveys or data, ours is very regularly sampled with the exception of some data dropouts like losses of lock or losses of light resonance. So if I take the Fourier transform of this, I'll walk you through some properties of our average noise and frequency space. So this is amplitude of the strain noise on Y versus frequency. So you can see this classical structure of gravitational wave detectors where you have the noise, it comes sweeping in from low frequencies where we have our best sensitivity at about 100 hertz, and then increases again as a function of frequency. And there are 3 sort of fundamental frequency regimes that dominate, that govern the shape of this noise curve. So at lower frequencies, we're most dominated, most limited by ground motion, so direct mechanical coupling between the motion of the ground and the relative motion of our optics. In the middle, in our most sensitive frequency regime, we will be limited by thermal noise. So this is actually the Brownian motion of the molecules on the optics is interfering with our relative displacement measurement. So think on that for a moment to really get a sense of the scale of the relative measurement that we're making. So we will come to rest on that fundamental limit once we hit design sensitivity. We're not quite there yet. We are fully quantum limited above about 50 hertz by shot noise. So this is this quantum photon noise. We're essentially counting photons, as that's the fundamental measurement that we're making to sense space-time strain, and that introduces the statistical fluctuations, quantum property of light. So this is what yields this basic structure, this basic shape. You'll notice also these very strong sinusoidal features in the data as well. So these are largely very well understood. We have the classic 60 hertz line, so this is AC power in the US. For the Virgo detector, it's at 50 hertz, so we have to watch out for that. We also have these sharp mechanical modes. So these are what we call violin modes, these mechanical resonances of the suspensions that are holding our optics. And you'll see a smattering of other lines. This fairly wide-looking series of peaks is a series of calibration lines, for example. But what we do when we try to analyze this data for transient gravitational waves is we whiten our data. So the lines don't bother us as much. What's going to most impact the background, what we're going to accumulate a lot of background noise from, is noise that looks like the signal we're trying to find, so transient noise. So what you're looking at here, so this is a day-long plot. So this is time, 24 hours on the x-axis, frequency on the y-axis, and each one of the dots you're seeing, so this is a basis projection of our data onto a series of sine Gaussian planes. So a wavelet transformation. Each one of these dots is a burst of excess power, essentially. And the color is the signal-to-noise ratio. And you can take away a few features from glancing at this plot. So we have this kind of smattering of very loud glitches that are happening at about hundreds or so hertz. That's their central frequency. We have a much higher rate of glitching below about 50 hertz. So this is actually due to light scattering. So this is from it's only from about a week or so ago. So this is O3 data. You can also see more faintly in lighter colors this much higher density of bursts of excess power here as well. So we get a lot of information from visualizations of our data like this, and it's artifacts like this in the data that are most harmful to our searches for transient gravitational waves. So I have a guessing game prepared for you. So here is a new noise feature to O3. I think I've told this group about ravens. I've told you about the phone. I think I've told you about the refrigerator as well. So this is a new one. So you're looking here. So this is time in minutes, where this is a 10-minute long plot. You have frequency on the y-axis, roughly the same axis on both of these plots. So up at the top is a gravitational wave strain data for LIGO-Hanford, and this is a microphone near the input optics. And you see this very harmonic-looking structure that decreases in frequency over time. Does anyone want to have a guess at what that is? That's coupling so nicely into our gravitational wave strain data. Kent knows. We have a guess over here? That's a very good guess, but it's actually a helicopter. This is a Chinook military helicopter. What you're seeing here is the Doppler effect. And this is the point of closest approach where it's coupling the most strongly, just as it changes in frequency. So this is a Chinook helicopter flying right overhead the control room. No, this was the first time I've ever seen it or heard of it. And so I've been with the collaboration for about 12 years. Planes, yes, very often, but helicopters are much closer and couple pretty well, as it turns out. Okay, so with all of that in mind, how do we search for signals in our data? And VJ did a really beautiful job introducing templates and waveform approximates. So I'm going to glaze over that a bit and say that we build a bank of waveform templates. So here's a template bank from O1 that's projected onto the basis of what we call mass 1 and mass 2. So here we define mass 1 to be the heavier of the two component objects, and mass 2 is the lighter. We can also reduce the computational expense of our analysis a little bit further if we make these astrophysically motivated spin constraints, which we choose to do for neutron star-like objects, where we have those spin measurements. So we populate our template bank. So this is about 250,000 templates. And for each one of these templates, what we're going to do is we're going to compare it to our data. So our sample data is here in blue. So this is the amplitude versus time. And this is a low signal-to-noise ratio, or low amplitude, I should say. A low amplitude signal that's buried in my noise. And what I'm going to do for each one of the templates in my template bank is I'm going to drag it across the data, and I'm going to compute this cross-correlation. And this is going to be directly related to the signal-to-noise ratio that I use to define how loud or strong my signal is. So let's see what this looks like. You might notice, especially if you're sitting close to the front of the room, that the template that I'm dragging across my data and the signal is not an exact match for the signal that's buried in my data. But as Vijay pointed out, the mismatch is fairly low here. So this is my match filtering process at a very basic level to first order. I'm computing this cross-correlation, and this is related to the signal-to-noise ratio that I'm searching for in my data. So a challenge with this, so a signal-to-noise ratio computed with this cross-correlation, all I'm essentially doing is taking the inner product between my model and my data. So if I have a very loud spike in my data and I'm taking the inner product with my model, I'm still going to see an artificially high signal-to-noise ratio. So to give you some examples, more real-life cases of data quality artifacts in LIGO detectors. So here on the left, these are our two most problematic types of noise. So on top, they have very different timescales. And on top, this plot is on the order of milliseconds. And on the bottom, this is on the order of tens of seconds. So this spans 200 seconds, and this is only about 200 milliseconds. So the plot up top, you might have heard, if you've seen a LIGO talk before, someone mentioned a blip glitch. And these are particularly insidious because you might notice that the time frequency morphology is essentially indistinguishable from a very heavy total mass system with anti-aligned spin. It's very difficult for our match filter algorithms to distinguish this particular type of noise from that particular type of compact binary coalescence that we are searching for. Meanwhile, on the bottom, so here we have this very long, much longer duration structure. So this is about 2 minutes long, and it has this sort of broad cadence. So it sort of increases in frequency and then decreases, but it has also this harmonic substructure within it. We think that this is related to highly nonlinear light scattering. So this is related to the motion of some surface that's scattering light that's recoupling with the main beam and making this series of beat notes. But these affect very different regions of our template bank. So here we have contamination for short duration searches, and here we have contamination for long duration searches. And this is pushing out the background, our noise background that we're comparing our signal-to-noise ratio to. This is limiting the effective sensitivity of our searches. Meanwhile, on the right, this is a famous case that we had. So this is the real raw data for LIGO Livingston at the time of the BNS detection during R2. So this is the August 17th, 2017 event. So you can see very clearly the trace of the neutron star signal behind it. And then you have this very, very loud glitch. So what we did to excise this by hand on the scale of tens of minutes from when we detected, when we noticed the signal was there, is first we applied this inverse Tukey window that you see here in gray. And that is what was used to generate the first sky map that was used to discover the counterpart. To do a more precise extraction, we modeled the glitch with wavelets. So these are more like Gabor wavelets. And this is what you see here in blue, and then we subtracted that from the time series. So a much less invasive procedure. And that's what was used to estimate the source properties that you now see in all of the papers from the LIGO collaboration that include this event. So more generally, what we can do to gauge whether or not this is a glitch or is this a real signal is what we call the chi-square test. And this is a pretty powerful method. So essentially, what you do, you can do it either in the time domain or the frequency domain. It's completely equivalent. But you divide your signal up into portions that have equal SNR. And then your chi-squared is defined as the sum for each one of these portions, how much that portion, how much you see, SNR that you see in that portion of the signal compared to how much you expect to see. So if this were a really loud glitch and I calculated my chi-squared, I would get a very high value. If it's a true signal and I see that this behaves exactly as I would expect my model to behave, I'll get a chi-squared of 1. So what we do is we re-weight this detection statistic. So we take our original detection statistic, signal-to-noise ratio, which again is related to this cross-correlation between my model and my data. And if chi-squared is about equal to 1, then we do nothing. It doesn't have an effect. If chi-squared, however, is greater than 1, then I introduce this down-weighting factor. And there are a couple examples here. So this is for the very first detection. So this is GW 150914, a time series of unweighted signal-to-noise ratio, that's in blue. And then you have this, we call it the new SNR, this chi-squared weighted SNR in purple, and then chi-squared itself in green. So you can see as my model is going over my data, I'm seeing more and more power where I don't expect to see it until I have this very good alignment with the real signal, and then it pops back up again. But at the peak of the signal, there's essentially no difference between my signal-to-noise ratio and my reweighted signal-to-noise ratio. So this is a powerful distinguisher for us between signal and noise. And then, of course, I would be remiss not to mention our searches that do not employ matched filter techniques. So this is one example. This is our flagship unmodeled burst search, coherent wave burst. So essentially what you're doing is you're taking your data and you're projecting it onto a series of wavelets. So in this case, it's Meyer wavelets. And you're looking for coherent power across your detector network. And then you also need to take into account the different time delays that you'd get from different positions of the sky. So this is clustered to find the maximum likelihood over all potential sky positions and all coherent power across however many N detectors you have in your network. For us right now in O3, it's the 2 LIGO detectors and the Virgo detector, assuming that they're all online and taking data. So there are a few vectors for data quality information that are available to the searches in low latency. So for those of you who are interested in open public alerts from the gravitational wave detector network, these are informed by a few tools where we've taken all of the data quality information and compressed it down to a certain set of vectors. So the first of the ones that I want to tell you about is called IDQ. So this is essentially a time series of the probability that there's a glitch in your gravitational wave strain channel, given the information in the auxiliary channels that measure the environment, the behavior of your detector, the power in your photodiodes, the control signals that you're using to push on your mirrors. 200,000 different time series could go in here. This is down selected to about hundreds, on the order of hundreds of channels. But essentially, you get as a function of time the probability that there's a glitch in H of t without any information, without intaking any information about H of t itself. Thank you. So here's an example of IDQ output. So this is a glitch very similar to the glitch for August 17th, our BNS event. So you have this spectrogram of our gravitational wave strain data. You have which is a glitch. And then a spectrogram of this witness channel. So if this happens to be an alignment sensing and control channel that's stationed at this anti-symmetric port, which is just a little bit south of the beam splitter, if you remember the layout. We see that our data quality vector witnesses this. So our data quality vector is essentially looking for spikes in the time series of problematic witnesses that it knows about. So there's just only 3 of them for this run, and this witnesses saturations of a control signal for the major mirror that we're using to sense gravitational wave strain. So we see, yes, there is a saturation here, and this also is witnessed by several other auxiliary channels, and this is all packaged with the frames now. So all of the low latency searches have access to information like this. Here's another very interesting example that I will skip for the moment, because I think we're running a little low on time. I also wanted to mention citizen science and machine learning. So I talked about this a bit at the last meeting, I think. So this is a very powerful collaboration between citizen scientists, and their goal is to form a training set. So we have a series of experts that generate the initial labels for about 20 different classes of glitches in the LIGO detectors and now the Virgo detectors. And then citizen scientists are trained to take those examples and further classify these glitches. This produces on the order of tens of thousands of training examples, which we can then feed into a CNN and use that to classify all the examples of transient noise that we have in an observing run. It's been a very, very powerful tool. And so very well related to the discussion we were having earlier, so this project was also funded to produce a lot of very useful infrastructure and architecture that scientists can use to query and go grab labeled glitches with some likelihood that they belong to a particular class. And that's been very, very useful as well. So that has brought us to now. All of this combination of data quality information has resulted in 11 detections for the first and second observing runs that I assume you have heard a lot about already. But particularly, you'll notice we have 2 match filter searches here that we're reporting false alarm rates for, and then also this unmodeled search that has witnessed many of these events with very significant false alarms rates as well. And then to date, we have 14 unretracted events in, well, a higher number of weeks now. So this is just from 03, assuming that the false alarm rates for some of these more likely events hold up for the catalog that we eventually publish. We have just about doubled our event count in 03. And then I wanted to take the last few minutes to jump back and talk about maximizing duty cycle. So this is a project that Ashish mentioned that's focused on improving sky localization. So what you're looking at here, this is the duty factor for 3 interferometers in green. So you need 3 interferometers to localize your signal well in the sky. And then 2 in blue. So 2 is what you need to confidently detect a signal. And then you'll see that we get less than 50% duty cycle so far in 03 for triple interferometer time. And the reason has a lot to do with this pie chart down here. So this is for the Livingston detector only. So green is observing mode, yellow is trying to lock, and then brown, which is what I'm going to focus on, and these 2 are related to each other, is environmentally caused. So there's something in the environment that is causing us to not be in lock. So often this is ground motion. So what you're looking at the top plot, so this is the binary neutron star range for LIGO Livingston, and this dropout here is a lock loss. This is where we're unable to maintain light resonance in the detector, and this is correlated with the spike in ground motion. So this is 0.03 hertz to 0.1 hertz. This is the best band-limited range for us to sense earthquakes. So you see this is a big earthquake, it shakes the mirrors around, and we lose light resonance. So a project that Ashish and I worked with a summer student, Ion, on last summer was a study of about 1,000 lock loss times, and our goals were to diagnose, why is this happening? Can we tell which points in the interferometer are most susceptible to this? And then can we predict it before it happens and leverage our advanced knowledge to change the state of the interferometer and prevent it? So we had 3 different machine learning approaches, each with different feature sets. So we would take a time series and transform it into DMTT, which Ashish and Matthew have both mentioned. And then our first approach was to use t-SNE, so unclustered or unsupervised clustering. And we found something very surprising, which was that if you use channels that monitor the actuation strength or the photodiodes that are trying to keep the mirrors locked, the light resonance in these cavities, this is a much better predictor of lock loss than ground motion. So this is the traditional thought, was that if you looked at the ground motion channels, you'd be able to predict the lock losses, but we found no correlation with earthquake channels or wind or anthropogenic noise. None of them seem to produce a viable pattern. And this is a very big surprise to us. So we also used random forests, again with DMTT features. We found if we combined channels, so different auxiliary sensors that are monitoring different auxiliary cavities, so the input mode cleaner, for example, or the signal recycling cavity, or the power recycling cavity, if we combine these, we achieved a very high accuracy, so about 95%. And then finally, we also tried convolutional neural net, again, with DMTT, this time stacked for different combinations of channels. And we were able, if we included all of the channels that we looked at, so on the order of 15 or so, over 98% accuracy. So this has been very promising. So just a subset of channels we found accurately predict over 97% of all lock losses. So this is isolating particular points within the detector that we can then go and diagnose to see why this is happening. So we were also able to use these 3 channels to accurately predict lock losses 10 to 15 seconds prior to when they were happening. And again, the big surprise, the ground motion channels are not good feature sets to predict lock loss. And then I'll leave my conclusions up, and I'm very happy to take any questions.